So anytime you hear heat, anytime you hear heat, you hear about heat and all these heat transfers, you have to, remember that thermodynamics should definitely come to play, because thermodynamics is the study of heat transfer. So from the first law of thermodynamics, we came to this particular law states that the change in total energy per unit mass, that is change in E, should be equal to Q minus W. Change in E is equal to Q minus W, where our Q is the total energy absorbed per unit mass, the total energy absorbed per unit mass. So whether you are considering a product or you are considering a raw material, the total energy absorbed per unit mass of, let's say, that particular raw material is giving us what? Q. And then this minus W. The W is the work done on the surrounding by the system. So the system will do work. So the work done by the system on the surrounding is giving us what? W. So when we move forward, we will talk about this particular work. It comes in two forms. We have what we call the PV work and then the shaft or the pump work. I'll talk about all these things when I move forward. So we also have this particular equation that total energy per unit mass is given as mechanical energy plus internal energy. And we know mechanical energy to be equal to kinetic energy plus potential energy. So mathematically, we can have this particular equation, that is E, to be equal to Ke plus Pe plus U, where Ke is kinetic energy, Pe is potential energy, and then the U is our internal energy. But we know from the kinetic energy formula that kinetic energy is equal to half of mass multiplying velocity squared. So half mv squared. And since we are considering a unit mass, don't forget that we are considering what? A unit mass. And anytime we are considering a unit mass, then we consider our m to be equal to 1. So hence, the kinetic energy will turn out to be half of v squared. And half of v squared is the same as v squared over 2. And also, potential energy is giving us mass multiplying gravity and then multiplying height. So our M here represents the mass, the G represents the gravity, and then the Z represents our height. And since we are considering a unit mass, then our PE will be equal to Z multiplying G. I hope you have followed up to this particular point. So let's continue. So if we are to fix in these, into the equation that we had, that is, if you are to fix the value for kinetic energy and that's for potential energy into the equation that is highlighted red here, we will get E to be equal to V squared over 2 plus ZG plus U, where V squared over 2 represents kinetic energy, that is Ke, and then ZG represents Pe, that is potential energy, and all these plus U. So if we are to perform changes in total energy, if you are to write equation for changes in total energy, it is just a matter of introducing the changes sign to, the E direction. Like we have to introduce the sign for change to the left side and then the sign for change to the right side as well. So our change in E should be equal to change in whatever found on the right side of the equation. So change in E should be equal to change in V squared over 2 plus ZG plus what? U. So we can call this equation 1. We can call this equation 1. Don't forget that we can call this equation 2. Don't forget that equation 1 stated that change in E is equal to Q minus W. That was our equation 1. And our equation 2 is what? Change in E is equal to V squared over 2 plus ZJ plus U. So these are the two equations we are having so far. So let's move on. So we are still on the first law of thermodynamics, that particular equation, stating that change in E is equal to Q minus W. So we saw that there is W found in the equation. That is the work done by the system on the surrounding. So the system does two main forms of work. We have what we call the PV work and then the shaft work or the pump work. So the PV work is like it is the form of work done by a fluid. So when you have a particular fluid and then it starts expanding, when you have a liquid or a gas in a particular tube or a particular container, and then it starts expanding or compressing, like it performs a particular energy called the pressure volume work or the PV work. And we also have what you call the shaft work or the pump work. So when you have a particular fluid in, let's say, a given container or in a given tube, and you want to pump that liquid from one location or from one point to another, you need a pump to do that particular work. So the work done by the pump is giving us what? The pump work, which is WS. And then the PV work is what? The work done by the fluid as it expands or compresses. So these two will come together to form what you call the work done by the system on the surrounding. So we can then, expand this particular or we can fix this particular into our equation 1. So from the equation 1, we learned that change in E is equal to Q minus W. And right now we have seen that W is given as PV plus WS. So let's fix PV plus WX into where we found W from the equation 1. Okay, we are just fixing the W plus PV, the PV plus WS into our equation 1. So when we fix this into the equation 1, we are going to get Q minus into brackets PV plus WS, where PV plus WS is equal to what? W. So when the negative sign enters the brackets, we are going to get Q minus PV minus WS. So this becomes our equation 3. So let's also consider something called enthalpy. Let's consider the total heat content of a particular system. When you have a particular system, the total heat content of the system is called enthalpy. And enthalpy is given by the formula U plus PV. Enthalpy is given as U plus PV. So from the equation number 2, we had our change in E to be equal to change in V squared over 2 plus Zg plus the U, where the U was our internal energy. So far as U was found in that particular equation, then let's try to make U the subject of the enthalpy equation. So we have U to be equal to H minus PV, and this becomes our equation 4. So we can now fix this particular equation, that is a U minus PV, into the equation number 2. So wherever we will see U, we are just going to write the value H minus PV in place of that. So we are now going to have change in E to be equal to change in V squared over 2 plus Zj plus H minus PV. We just substituted our equation 4 into the previous equation 2 that we had. So at the end, we can now confidently equate equation 3 to equation number 5, because from equation 3, we had change in E to be equal to Q minus PV minus WS. So we are just equating change in E to change in E. Equation 5 is having change in E, and then equation 3 was also having change in E. So it means that we can equate each of them to each other. So when you do the equation, we are going to get change in V squared over 2 plus Zj plus H minus PV to be equal to Q minus PV minus WS. So since we have minus PV on the left side of the equation and then minus PV on the right side of the equation, then they can cancel each other. And at the end, we are going to have change in V squared over 2 plus Zj plus H, and all these should be equal to Q minus WS. So this is the heat balance equation. This equation highlighted in red here is the heat balance equation. So please, in case you can't even remember the way we do we prove the formula, at least have this formula in your mind. Always take note that when the question says that heat is given out to the surrounding, then the Q should be negative. Take note of that. When you read the question and the question says that heat was rejected or heat was given to the system, like heat was given out to the surrounding, then Q should be negative. And also when the question says that heat was added to the feed, then the Q becomes positive. So we are about to start the calculation. But before we start the calculation, let's learn something briefly about the steam table. The steam table gives us an insight of, or like it just gives us an insight of the temperatures and then the various phases of water. So with this, we'll be able to know the heat content of a particular liquid water or a steam water, or like a liquid water or a vapor, saturated vapor, based on the temperature that we are given at hand. So sometimes the question will just make mention of the temperature of, the water. Okay, and when you are given something like that, just pick the temperature and then bring it to the steam table here to find the corresponding vapor, like the corresponding enthalpy, and then use it for the calculation. So one of the headache of many students is to devise whether to read from the saturated vapor column or to read from the liquid water column. This is where most students find it difficult. So when you are given the question, make sure that you have read the question well. In any given question, they will state it in the question that we are working with liquid water or we are working with a steam. Just pay close attention to the question and then deduce from the question whether you are giving liquid water or whether you are working with saturated vapor. And after doing that, you bring it to the table here to fish out the corresponding enthalpy value. So let's start doing the calculation so that you will appreciate what I am talking about. So let's consider this particular worked example. Water at 85 degrees Celsius is being stored in a large insulated tank at atmospheric pressure. It is being pumped at steady state from this tank at point 1 by pump at a rate of 0.567 meter cube per minute. The motor driving the pump supplies energy at a rate of 7.45 kilowatts. The water passes through a heat exchanger where it gives up 1408 kilowatts of heat. The cooled water is then delivered to a second large open tank, that is atmospheric pressure, at point 2, which is 20 meters above the first tank. So you have to calculate the final temperature of the final water delivered to the second tank, and you have to neglect any kinetic energy changes since the initial and then the final velocities in the tank were essentially zero. So let's try to break down this particular question before we even start solving it. So I have intentionally highlighted the cooled water. You see that I have highlighted the cooled water with what? Red ink. So this is to draw your attention to the fact that the water moving in the system is in the liquid state. So if you are to move to the steam table, then we will do the reading from the liquid water column. Take very good note of that. Take very good note of that. If we were to be working with steam, the question would have mentioned that. So please always pay close attention to the questions that you will be given. So first of all, let's use a diagram to represent the information given in the question. So this particular diagram summarizes the whole question. We were having a tank at a point 1, okay? So that particular point was at a ground level. That particular point was at a ground level. So that is why the initial height was given to be what? 0 meters. Although the question didn't say 0 meters, but we always take the initial height to be at ground level and hence equal to 0, unless the question states it that, let's say, the initial height was let's say 20 meters or let's say 50 meters. Unless the question states that, anytime the question didn't state that, let's say the initial height is this, just take it to be equal to 0 because we consider it to be at a ground level. And from the question, the water at the tank was initially at 85 degrees Celsius, but we don't know the heat content of that particular water. So that is why enthalpy is given to be what? I have introduced question mark in front of the enthalpy. And also, we use a pump to pump the water into a heat exchanger. So pump work, we don't know the pump work. That is why I have just introduced question mark in front of this. And also, in the heat exchanger, that is where the heat changes occurred. Let's get back to the question to see whether we lost heat or we gained heat. So from the third sentence, the question says that the water passes through a heat exchanger where it gives up. So it means that the system lost water to the surrounding. And so far as we are losing water, then our Q should be negative. Let's put this in our mind. We lost water. So that is why our Q is what? Negative. If the question stated that heat was added, then the Q would have been what? Positive. But the question said heat was what? Given up or heat was lost. Just take it to be what? Negative. And also, we don't know the second temperature because that is what we are looking for. And we don't know the total heat content of water in the second tank. And we were given the height from the height of the second tank, that is from where the second tank is to the ground level, to be equal to 20 meters. So I think we have all the parameters to start our calculation. So first of all, do not forget your heat balance equation. Just state it. This is very simple. Unlike mass balance that we have to, let's say, always consider arrows moving towards the system and then equating it to arrows away from the system. Here we have a fixed formula. Just quote the formula and then start looking for the needed parameters and then fix them in the equation. So when we are to expand this same formula here, I am just trying to expand the heat balance equation for you to appreciate it very well. So when you expand the equation, we can see that it will be change in V squared over 2 plus change in Zg. The change should just enter the bracket, okay? The change symbol here should just enter the bracket. That is why I'm having change in V squared over 2 plus change in Z plus change in H, and it should be equal to Q minus Ws. This same equation can further be expanded to be V2 squared over 2 minus V1 squared over 2. You see, I am just expanding it further, because change in v squared over 2 can be considered as the final, and then change in final velocity squared over 2 minus minus the initial velocity squared over 2. And also the change in z is the same as the change in initial potential, the change in the change in the initial and then the final potential energies. So that is final potential energy minus the initial potential energy. And then the H2 minus H1 here represents our final enthalpy minus the initial enthalpy. And all these should be equal to Q minus Ws. I have just expanded the formula highlighted red here. So please don't be confused here. So from the question, we were given the V1 and the V2 to be equal to 0. The question stated that the initial and then the final velocities were 0. So don't forget that. And also I said that anytime the question didn't state that, let's say initial height is 50 or so, just take the initial height, that is Z1, to be 0. Take it to be at the ground level and hence to be equal to what? 0. And the question also made mention of the fact that the height of the second tank is equal to 20 meters. And then the initial temperature of the water in the first tank was also given to be equal to, 85 degrees Celsius. But we don't know the corresponding H1. We don't know the corresponding H1, that is the initial enthalpy. So let's try to use this particular temperature here, that's the T1, to find the corresponding enthalpy value from the steam table. We can get the H1 from the steam table by using the temperature that we have here. So the steam table is very helpful. When you are given a temperature and then you don't know the corresponding enthalpy value, just pick the temperature, go to the steam table, and use it to look for the corresponding enthalpy. Likewise, when you have your enthalpy and then you don't know the corresponding temperature, just pick the enthalpy value and then take it to the steam table and use it to look for the corresponding temperature value. So let's come to the steam table here. So the initial temperature was given to be 85 degrees Celsius. This is the temperature given to us. So this is the temperature of the cooled water, like the enthalpy of the cooled water that entered the system. So it was given to be 85 degrees Celsius. So we are going to use the 85 degrees Celsius to look for the corresponding enthalpy value. So when you look at the steam table here, we can see from the 85 degrees Celsius column that we have 355.90 and then the 2 says 51.9 here. So I said from the question that we are working with cooled water. This is why I keep on saying that anytime you are given the question, read it well to find out whether you are working with a steam or we are working with what? A liquid water. So since we are working with cooled water, then the water is at a liquid state, and hence we will pick the 355.90, which is at the liquid water column. So hence our enthalpy will be equal to 355.90 kilojoule per kilogram. This is the same as 3559 times 10 to the power 3 joule per kilogram. Joule per Kelvin. The point shouldn't be here. There shouldn't be any point here. So it should be 3559 times 10 to the power 3 joule per Kelvin. So we have gotten our enthalpy, and we can then move on to perform the calculation. So from the formula, from the heat balance formula, this is how it looks like. So let's ask ourselves, which of the parameters are we not having so far? We are having the V1 and the V2 to be 0. We are also having the Z1 and then the Z2 already. And we have also gotten our temperature. We have also gotten our initial and then the final temperatures. Okay, no, we've gotten our initial enthalpy, but we don't know the final enthalpy. So we can then use it to find our final enthalpy. And also let's ask ourselves, were we given Q and then Ws in the question? Let's ask ourselves that question. If we were given this, then we are good to go. So let's try to find out whether we were given all these in the question. So we know Q to be the heat absorbed per unit mass. Q is the heat absorbed per unit mass. So for the Q is written with respect to a unit mass. Q is written with respect to a unit mass, but not the total heat, or the total heat absorbed in the system, or the total heat rejected in the system. Anytime we make mention of heat, we make mention of Q, we are talking about the heat absorbed per unit mass. And unit mass is the same as what? A flow rate, okay? The unit mass was the same as the flow rate, and the flow rate was given in the question to be equal to 0.567 meter cube per hour. This value is the flow rate. So if you want to get our Q, we have to just divide the total heat absorbed by the flow rate to get our Q. But before then, the unit for the flow rate was given in meter cube per hour. Try to do the conversion. Try to do the conversion from meter cube per hour to, kilogram per second. And that is done by multiplying it by 1,000 and then 1 over 60. When you multiply it by 1,000 and then 1 over 60, then you'll be able to convert it from the meter cube per hour to kilogram per second. So please don't forget this particular conversion as well. I have made mention of two different conversions now. I first of all made mention of conversion from kilogram per hour to kilogram per second. And what I said is that you have to just multiply whatever you were given by 1 over 3,600, or in other words, just divide it by 3,600, and you'll be able to do that. And for here too, we are converting it from meter cube per hour to kilogram per second, and that is done by multiplying it by 1,000 and then by 1 out of 60. So, as I said, our Q is giving us the total heat absorbed per the flow rate. So we have to just divide this value given in the question. That's the 1408 kilojoule per second by the flow rate, which is 9.45 kilogram per second. So when you do the division, you are going to get 148.99 times 10 to the power 3 joule per kilogram. And don't forget that the system gave up heat. The system gave up heat. That is, the system lost heat. So we have to introduce negative sign in front of our Q value here. And also, the pump work is the work done by the pump in what? Pumping the fluid from one point to another. So here, we can get this by dividing the power of the pump by the flow rate to get our pump work. The pump work is giving us what? Power over what? The flow rate. So the power of the pump was given to be 7.45 times 10 to the power 3 joule per second. And by dividing it by the flow rate, we will get our shaft work or the pump work. So I think we have now gotten all the parameters. We have gotten all the parameters that we can fix it into the general heat balance equation to work out our final enthalpy, and then based on the final enthalpy value to work out our final temperature in the second tank. So, as I said, the change in v square, like the change in velocity, should be 0 because initial and then final velocities were 0. So it should be 0 plus our final height. The height of the second tank was given to be 20. I am just fixing the values into this particular expanded formula. So don't be confused. I am just fixing the various parameters that we have gotten from the question into the expanded formula to work out the H2. So it will be 20 multiplying the gravity. 20 multiplying the gravity, that is Z2 is giving us 20, and then gravity was also given in the question to be 9.81. So when you fix them in here, we are going to get 20 multiplying 9.81 minus 0 multiplying 9.81, and all this plus H2 minus 355.9 times 10 to the power 3. And all this should be equal to the Q. We were given, we had the Q to be equal to 148.995 times 10 raised to the power 3. If you remember, I made mention of the fact that the system gave up heat. So Q should be negative. And also the shaft work should be negative. The shaft work itself should be negative because the system gave up heat to the surrounding. So when you compute the whole of this, you are going to get your H2 to be equal to 207.497 times 10 to the power 3 joule per kilogram. And when you convert this to kilojoules, you are going to get 207.497 kilojoule per Kelvin. So this becomes our enthalpy of the, this becomes our enthalpy of the water in the second tank. But the question demanded us to work out the final temperature, but not the final enthalpy. So let's just pick this particular value to look out for the corresponding temperature from the steam table. So when you pick 207.497 kilojoule per Kelvin to the steam table, let's start looking for where we can find this value from. So when we look at the steam table, we can see that there is no 207 indicated on the table. We can't find 207 on the table. Like, we can't find that particular value from the table. But we can all agree to the fact that 207 is closer to 209. And it is also closer to 188 when you consider the table. So it means that 207.497 can be found between 188.45 and then 209.33. This value can be found in between the two. So we are now going to base on these two to work out the corresponding temperature. We are going to base on these two to work out the corresponding temperature for the 207.497 kilojoule per Kelvin. So here we do it like the way we find gradients. We do it like the way we find gradients. So always make sure that the one that you are looking for is found in between two known figures. Make sure that it is found in between two known figures. So we can see that the 207.497 can be found between 188.45 and then 209.33. So let's T1 to be equal to the one on top of the figure you are looking for. Let's make T1 to be equal to the one on top of what we are looking for. So the corresponding H value, that is H1, should be equal to 188.45. And then the one below it, the one just below it, or like the immediate bigger number than that, should be equal to T3. So the T3 will be 50, and then the corresponding H3 will be 209.33 kilojoule per Kelvin. Please don't be confused. I have just took the values from the table, and then the one above the number we are looking for is denoted T1 and then H1, whereas the one immediately below the number we are looking for is denoted T3 and then H3. So after reaching this point, we are just going to, based on these two, to look for to look for that of the H2 and then the T2. So it works like the way we find gradients. It works like the way we find gradients of a line. So change in y over change in x is always constant. The change in y over the change in x is always constant. So we can say that T2 minus T1 over H2 minus H1 should be equal to T3 minus T2 all over H3 minus H2. Make it this way. Middle, like the middle number, okay, minus number on top of it, divided by the middle number minus the number on top of it. We are writing it in terms of the temperature and then the enthalpy. So the enthalpy of the middle number, that the one that we are looking for, okay, minus the enthalpy of the one on top of it, divided by the temperature of the middle number minus the temperature of the number on top of it, should be equal to the enthalpy of the last, or like the bottom number, minus the middle number, all over that of what, the temperature of the middle, or the temperature of the bottom number minus that of the middle number. You can make it, you can write them interchangeably. You can make the enthalpy values come on top and then the temperature values become the denominator, or you can reverse it. Any way you do it, you are right. You can make temperature the numerator and then H the denominator, and then vice versa. So please don't be confused. Middle numbers, we just we are looking for the middle number. Always make sure that the one that you are looking for has been in the middle. When you consider from the table, make sure that the one you are looking for will be sandwiched between two numbers. So the one that you are looking for, the temperature of the one you are looking for, that is T2 minus T1 all over the H2 minus H1. It should be equal to the temperature of the number below it. That's the bigger number below it. Okay, that's T3 minus T2 all over H3 minus what? That of the H2. So let's start putting in the figures into the formula, and after doing that and then computing it, we can get our T2 to be equal to 49.56 degrees Celsius. So this is the final temperature of the water in the second tank. So this is the value that we will get. So that is that. This is how we do the calculation. So anytime you are giving such a question, just follow like similar procedure and then use it for the calculation. Let's try this particular simple example and then end it here. Let's try this particular example and then end the tutorial session here. So this is the example. Water enters a boiler at 22.00 degrees Celsius at atmospheric pressure through a pipe at an average velocity of 3.20 meter per second. The exit steam is at a height of 22 meters above the liquid inlet, and then is it above the liquid, and then the inlet steady state heat added was given as 2689.81 joule per Kelvin, and you are to determine the final temperature of the steam. I intentionally added exit steam. I intentionally added the word exit steam for you to understand that with this particular question, we are working with what? A steam, but not liquid. So when you're to read from the steam table, read from the steam column. Don't read from the liquid column. And also, I have highlighted the added. Added is also highlighted because I want you to understand that heat was added to the water flowing in the system. So anytime we add heat to the feed, then K becomes positive. And when we reject, then the K becomes what? Negative. So don't forget all these things. And the question also made mention of the fact that we are working with what? Steady state. So since we are working with steady state and then since we are working with steady state and then no pump was even mentioned in the question, then we can boldly say that no pump work is what? Is done. No pump work is done. When the question makes mention of the fact that we are working under steady state, then pump work becomes zero. And also when the question didn't state or like didn't make mention of pump, like we using pump to pump any feed through the system, then pump work should also be what? Should be zero. So I think we can now move on to start performing the calculations. So as I said, use a diagram to represent the question. So this particular question, this is how the diagram will look like. We don't have a fixed diagram for, heat balance. Unlike mass balance that we have a fixed diagram. We don't have a fixed diagram. We just draw the diagram based on what you are reading from the question. So we can see from the question that water entered the system and the water was at a temperature of 22 degrees Celsius and then heat was added. So that is why Q is given to be positive 2689.81. And then we are looking for the exit steam and then the height from the exit steam to the ground level was given to be 22 meters. So you see, we can see from this question that the question didn't make mention of any flow rates. So since the question didn't make mention of flow rates, then we can just pick the Q value here and then use it for our calculation. We can just pick the Q and then use it for the calculation since the question didn't make mention of anything like flow rates. So let's come back to the question. We can then use the heat balance equation to do our calculation. This is the golden formula that we'll be using. Always just quote the formula and then look out or like find out whether you have all the needed parameters, fix them in, compute it for the H2, and then use the H2 to find the corresponding temperature from the steam table. As simple as that. That's how we do it. So let's continue. So the question gave us the average velocity to be equal to 3.20 meter per second. The question didn't say that we have initial velocity or maybe final velocity, but we were rather given average velocity. So since we were given average velocity, then we can just use it for the v squared over 2 portion to get 5.12 meter squared per second squared. So this becomes our average. This becomes our v squared over 2. This becomes the figure for the v squared over 2. Now let's move on to talk about the change in potential energy. So the final temperature was given to be height was given to be 22 meters, whereas the initial height wasn't mentioned, but we consider it to be at ground level. So since we consider it to be at ground level, then it should be equal to what? 0. So when you complete this, we can get our change in potential energy to be equal to 215.82 joules. So we can now, based on the initial temperature given, to look out for the corresponding enthalpy from the steam table. So let's go to the steam table. So let's make T1 to be equal to 22 degrees Celsius because that is what you are looking for. We don't know the T1. So let's make it equal to 22 degrees Celsius. And then we can see that 22 degrees Celsius is found in between 21 and then 24. 22 degrees Celsius is found in between 21 and 24. We can't directly get 22 from the steam table, but we have 21 and then 24. So 22 is found in between 21 and then 24. So we can make, let's say, 21 the T2 and then the 24 being our T3. You don't necessarily have to make, let's say, the one in the middle always being T2 and then the one on top being T1. No, you can just do it anyhow, but just make sure that it won't, skip you. Just pay close attention to it so that you won't mix things up. So, as I said, always make sure that it's like you are finding gradient. So, always the number in the middle minus the number on top, like the change in temperature between the number in the middle and then that on top, or over change in enthalpy between the number in the middle and then the one on top should be equal to the change in temperature between the number at the bottom minus the one in the middle, all over changes in what? Enthalpy between the number at the bottom and then the number in the middle. So that is what we are going to do. You can also, turn this particular equation upside down. No matter the way you do it, you get the same answer. So when you start fixing in the values, we are going to get our H1 to be equal to 2541.7 kilojoule per kilogram. 2541.7 kilojoule per kilogram. So this becomes our H1. So since we are having H1, we can, this particular value is the same as 2541.7 times 10 to the power 3 joule per kilogram. And the question also stated that heat was added. So since heat was added, then the Q is positive. And at steady state as well, our shaft work or the pump work is also given to be 0. So we can now fix the value. We cannot fix the values that we have given into we have gotten so far, or like the values given in the question into the heat balance equation to work out for the final enthalpy, and then use the final enthalpy to look for the corresponding final temperature. So we have already computed the V squared over 2 portion, and we had 5.12, and we have also computed the changes in potential energy, and we have 215.82, and we are now looking for the final enthalpy, that's the H2 minus our initial enthalpy, which was 2541.7 times 10 to the power 3, and all these should be equal to Q, that is 2689.81 minus 0, because shaft work is given to be 0. So when you complete the whole of this, you are going to get your H2 to be equal to 2544.2 kilojoule per kilogram. So this is the value that you are going to get for your H2. So after getting the H2, we can then use this particular value to look for the corresponding temperature from the steam table. So when you pick this value and then you go to the steam table, we can see that there is no 2544 found from the steam table, but this particular figure can be found in between 21 and then 24. So we can just bring this value in the middle and then look at the number on top of it and then the number below it, and use it to find the corresponding H, or like to find the corresponding T2. So I think I have already spoken about how this particular calculation is done, how we use the values to work out the corresponding ones from the steam table. I think I've mentioned this over and over. So hence I expect you to understand it, follow it, and then use it for the calculation. So that is that. So kindly try. So at the end of the day, we are going to get, try going through the calculation, and then you get you get your final temperature to be equal to 23.56 degrees Celsius. So that is that. Try this particular second question and then comment with your answer. Thank you very much for watching this video. Stay tuned for my other videos on heat transfer and then other biochemical engineering, biochemistry, and then molecular biology videos. Please don't forget to subscribe to my channel as well for me. See you another time.